Hey everyone, let's do example 5 very quickly, which says to do the same as before, but with a equals 5, negative 3, negative 7, 1. What we did before was this, which is to say, we're going to find beta, an ordered basis beta, consisting of vectors b1 and b2, and also the matrices P equals b1, b2, right? That's the matrix, 2 by 2 matrix. And D, which we established equaled T beta, which is going to equal the matrix consisting of the eigenvalues of A along the diagonal. Now, it's possible lambda 1 equals lambda 2 if if A has only one eigenvalue and has multiplicity 2, and it has an eigenspace of dimension 2. So let's see that. But such that A equals P D P inverse, or equivalently P T beta P inverse. So let's quickly do this. Find the characteristic polynomial of A. Set it equal to 0. You're going to find that it's 5 minus lambda times 1 minus lambda minus 21, which equals lambda squared minus 6 lambda minus 16, which of course equals 0. Actually, first let me factor that maybe. That's going to equal lambda plus 2, lambda minus 8, which equals 0 at lambda equals negative 2 and 8. So in fact, A has 2 eigenvalues. So at this point, we actually know A is diagonalizable because each eigenvalue has to have an eigenspace of dimension at least 1. So they both have eigenspaces of dimension 1. And so A is diagonalizable. Let's find the eigenspace real quick. For negative 2, A plus 2i is going to give us 7, negative 3, negative 7, 3. And I think we can see that that row reduces to 1, negative 3 sevenths, 0, 0. And so we get, so x1 equals 3 sevenths x2, but x2 is free. So really x1 equals 3 sevenths t. So the eigenspace for negative 2 equals the set of all, I guess you could say it's t times 3 sevenths 1 for all real numbers t. Again, we didn't actually have to find the eigenspace for negative 2, but we did need to find this vector, so it doesn't hurt too much to state the whole eigenspace. Anyway, do the same thing for A, and you get something pretty similar. This one works out pretty nicely. It's negative 3, negative 3, negative 7, negative 7, which I think we can see row reduces to 1, 1, 0, 0. So x1 equals negative x2, and of course x2 is free. And that, of course, means that the eigenspace for 8, again, we don't have to find the whole eigenspace, but why not? Negative 1, 1. All real numbers t. So again, we do need these 2 basis vectors, right? So again, make sure we answer the question. We want to find the basis b, right? That's what it was asking for. So beta equals, now remember, the order, it matters in the sense you can choose whichever order you want, but if we're going to order it this way, then that means that P equals the matrix, right, with just those vectors as the eigenvectors, and D, or T beta, equals the corresponding eigenvalues. We have to get that in the same order, right? If we had listed the vectors in the opposite order, then we would have had to list 8 and negative 2 in the opposite order. And just to point it out, A equals P D P inverse. That's all. Thanks.